Hi everyone, welcome to Go Classes. In this lecture, we will solve all the previous year exam questions from this topic countability, countable set, uncountable set. So all the previous year exam questions we are going to discuss, all the GATE exam questions, TIFR exam questions, NET exam, UGC NET exam, ISRO, NILIT. So all these exam questions we are going to discuss in this session. Okay. So let's start this session now. Before we start this session, I want to tell you that this complete countability playlist from Go Classes, okay, this complete playlist is available on the Go Classes YouTube channel. Okay, so you can just go to Go Classes YouTube channel or you can search on the YouTube Go Classes countability playlist. Okay, so you can search it and you can find the complete playlist. All the lectures are available. You can notice here. Okay, in this playlist, what we have covered, let me tell you. In this playlist, what we have covered the idea of cardinality, the definition of cardinality, the results related to cardinality. We have seen what is countable set, uncountable set, Cantor's diagonalization proof. Okay, using Cantor's diagonalization proof, we have proved many uncountable set. We have proved that set of real numbers is uncountable. Okay, so a lot of I can say a lot of uncountable set we have proven using Cantor's diagonalization proof. Okay, we have seen three definitions of countability. Okay, three different definitions of countability we have seen. Also, we have seen theorems for countable set. Okay, all the theorems like union of countable set is countable, subset of countable set is countable. Okay, cross product of two countable set is countable. So theorems related to countable set, that also we have seen. We have seen Cantor's theorem, also its consequences. Okay, also we have seen countability results in theory of computation. So remember, in this playlist you can find everything. You can easily notice here. Okay, so this playlist you can search on the YouTube. You can search this playlist, or you can go to Go Classes YouTube channel and you can find this playlist, this countability complete playlist you can find. Okay, so let's start now. Let's start the previous year exam questions from countability. So let's start with this GATE exam question. This is GATE Computer Science 1997 question from countable, uncountable set. Let's solve this. Let's see that sigma alphabet is given to you, that is A, B. Which of the following set is not countable? The question is asking which of the following set is not countable. So tell me what is the answer? Which of the following set is not countable? Set of all strings over sigma. Set of all strings over sigma. That is countable, right? Okay. Set of all strings over sigma. This is your sigma star. If you look at option A, this is your sigma star. And we know sigma star is countable. We already know sigma star, that is countable. Okay, so you can see this is countable. What about option B? Option B, what about option B? Option B is power set of sigma star, right? That is power set of sigma star, set of all languages. That is uncountable. Okay, that is uncountable. So remember, this is your answer. Your answer will be this, because this is uncountable. This is uncountable. Okay, option A is countable. Option A is sigma star. Sigma star is countable. But set of all languages, that is power set of sigma star, that is uncountable. What about set of all regular languages? What about set of all regular languages? That is countable. That is countable. What about set of all languages over sigma accepted by Turing machines? What about this? Set of all languages over sigma accepted by Turing machine. See, this is nothing but set of RE languages, right? This is set of all RE languages. This is set of all RE languages. Okay, what is set of all RE languages? This is also countable. Set of all RE languages, recursive enumerable languages. This is the set of all RE languages, recursive enumerable languages. This is also countable. So for this question, what will be the answer? For this question, the answer will be what? The answer will be option B. Option B is uncountable. Remaining all the options are countable. Now let's see some details. Okay, some proof. Let's see why option A is countable. Okay, let's see this option A. Let's focus on this option A. So this, if your sigma is A, B, this is your alphabet, then prove that, let's prove that set of all strings, set of all finite length strings, that is countable. Okay, prove that set of all strings, or I can say sigma star. Okay, prove that sigma star is countable. Prove that sigma star is countable. Prove that sigma star is countable. Remember, sigma star means set of all finite length strings, right? Yes or no? Set of all finite length strings. But remember, in theory of computation, by default, every string has what length? By default, what is the length of every string? Tell me. In sigma star, what we have? Let me know. In sigma star, we have finite length strings, right? Yes or no? We have finite length strings. So remember, in theory of computation, in this subject, theory of computation, in automata theory, every string has finite length. Agree with me? Every string has finite length. Okay, so you can see by default, every string has finite length. So you don't have to write it. You can simply say set of all strings. Set of all strings is countable. Set of all strings is countable. Okay, set of all strings is countable. Now remember one thing. I want to tell you one thing. Remember, if you look at strings in general, if you look at strings, then they can have infinite length. But that should be given in the question. Okay, that should be given in the question. So remember, in theory of computation, by default, what happens? Tell me. Every string has finite length, right? By default, every string has finite length. By default, every string has finite length. Every string has finite length. Correct? Okay. So remember, one thing you remember, set of all infinite length strings, that is actually uncountable. This we have seen. Yes or no? We know that set of all infinite length strings, that is uncountable. Set of all infinite length binary strings. Set of all infinite length binary strings. Set of all infinite length binary strings, that is what? Tell me. Is uncountable, right? This we have already seen. We have proven it using Cantor's diagonalization argument. Okay, this we already know, that set of all infinite length binary strings, that is uncountable. Okay, but remember, set of all finite length binary strings, and by default string has finite length. Okay, by default string has finite length. Set of all finite length binary string, that is countable. Okay, and remember this point, that by default, if I say string, then that has what length? By default, if I say string, then that automatically means finite length strings. Okay, so when I say string, that automatically means finite length strings. But if this is given in the question that you have infinite length strings, if this is given in the question that you have infinite length strings, then that is uncountable. Okay, we have proven it using Cantor's diagonalization argument. Okay, we have proved it. If you remember, we have proven it. Using Cantor's diagonalization argument. This Cantor's diagonalization argument. Okay, so this we have already seen, that set of all infinite length binary strings, that is uncountable, and we have proved it. Using Cantor's diagonalization proof. This we already know. Okay, so let's come to our question. That sigma star is countable. If your sigma is a comma b, then what is sigma star? Sigma star will be set of all binary strings. Okay, yes or no? That will be set of all binary strings, because your sigma is a comma b. So your sigma star will be set of all binary strings, and set of all binary strings, that is countable. Can you prove it? Let's prove it. What is the proof number 1? Tell me, what is the proof number 1? Let's prove it. What is the proof number 1? You can create a bijection between sigma star and set of natural numbers. Yes or no? We can create. What we can do? We can create a bijection. A one-to-one correspondence we can create. We can create a bijection between this sigma star and set of natural numbers. Yes or no? This bijection we can create. Okay, very easily you can create this bijection. See, first of all, what you do, in this sigma, you have a comma b. Just assume that a is 0. Okay, think of this a as 0 and think of this b as 1. Okay, so basically you consider this sigma equal to 0, 1. You consider this sigma. Now what you can do, you can create a bijection between sigma star, between all the binary strings and set of natural numbers. So how will you create that? I can create. So this is your sigma star. Here you have epsilon. Here you have 0, 1, 0, 0, 1, 1, 0, 1, 1. Okay. Here you have, for example, 0, 0. Okay. 0, 0, 1, and so on. 0, 1, 0, and so on. This is your sigma star. So can you create a bijection from set of from set of binary strings to set of natural numbers? How can you create? Tell me. How can you create? Let me know. How will you create? Will this work if I do this? Okay, if I do this, will it work? For example, if I do this, that f of w is decimal of w, will it work? Decimal of w. If will it work? Is this a bijection? If I do this, if I create this bijection, if I create this mapping, if I create this mapping, will it work? This mapping, will it work? Will it work? This mapping, will it work? Tell me. If I do this, f of w is equal to decimal of w. This is not even a function. This is not even a function, right? Yes or no? So this is not even a function. Why? This is not even a function from sigma star to set of natural numbers. From sigma star to set of natural number. Because remember, in the set of natural number, you have these 1, 2, 3, 4, 5. So tell me, if you do this, f of w equal to decimal of w. If you do this, then what the image of 0? What will be the image of 0? There is no image of 0, right? If you do this, then f0 does not exist. See, f0 does not exist. There is no image of 0. There is no image of 00. There is no image of 00, right? Yes or no? So you can see this is not even a function from sigma star to set of natural number. This is not even a function. If you do this, that f of w equal to decimal of w, this is not even a function, because what will be decimal of 0? What will be decimal of 00? Decimal of 00 will be 0. That is not here. That is not here. That is not in the codomain. So I can say there is no image of 00. There is no image of 000 also. There is no image of 000 also. Okay. So this is the idea. This is not even a function. So this will not work. So what will work? So what will work? Tell me. So what is going to work? Give me a bijection. I want a bijection. Give me a bijection. So tell me, from sigma star to set of natural number, give me a bijection. You can consider this bijection. What I can do? Fw is decimal of 1w. Fw is decimal of 1w. 1w means what you do? You put 1 before it. Decimal of 1w. Remember, you put 1 before it. Okay, Fw is decimal of 1w. This is what you do. Very simple. This is what you do. So remember, I want a bijection from sigma star to set of natural number. Okay, this is what I want. Then what I can do? I can give you this mapping. F of w is equal to decimal value of 1w. Decimal value of 1w. Okay, 1w. Just put 1 before it. This is what I can do. Now you can easily notice this will be bijection. This f will be bijection. This mapping is bijection. This is a bijective mapping. Remember, this is a bijective function. This is a bijective function from sigma star to set of natural number. From sigma star to set of natural numbers. Is this clear? Okay. Tell me, what will be the image of epsilon? What will be the image of epsilon? Let me know. What will be the image of epsilon? That will be decimal value of 1 epsilon. 1 dot epsilon. Okay. Okay. Because remember, Fw is decimal value of 1w. Just put 1 before it. So what will be this? What is the image of epsilon? That will be decimal value of 1 epsilon. 1 epsilon, that is simply as 1. So the decimal value of 1, that will be 1. Okay, so image of epsilon will be 1. Remember. Okay, image of epsilon, that will be 1. Image of epsilon, that is going to be 1. Right? Yes or no? Very simple. Okay, I hope you understood. So tell me, what will be this? Now, this is the function. We have created this mapping from sigma star. And what is your sigma? Your sigma is 0, 1, or you can think of it as a, b. Okay, you can think as a, b, where a is 0 and b is 1. You can think like this. Okay, you can think like this. So very simple. So this is the mapping we are giving, that f of w is equal to decimal value of 1w. Decimal value of 1w. Okay, this is the mapping we are giving. So what will be f of 0? That will be decimal value of 10. That will be decimal value of 10. What is the decimal value of 10? What is the decimal value of 10? That will be 2. Okay, what will be? Tell me, what will be f000? What is the image of f000? That will be decimal value of 000. That will be decimal value of 1000. Sorry, decimal value of 1000. Okay, just put 1 here. Okay, so because this is what you can see, just put 1 before it. So decimal value of 1000, that is 8. So very simple, you can easily notice that the image of 0, that will be 2, the image of 1, that will be 3, the image of 00, that will be 4, the image of this will be 5, the image of this will be 6, the image of this will be 7, the image of this will be 8, the image of this will be 9, the image of this will be 10, and so on. So tell me, can you notice this is a bijection? Okay, a beautiful bijection. This is a bijection, right? Yes or no? This F, this is a bijection. This is a bijection. Okay, this F, this is a bijection from sigma star to set of natural number. Sigma star to set of natural number, this is a bijection. You can notice. Okay, this is one-to-one correspondence. This is one-to-one correspondence from sigma star to set of natural numbers. We have one-to-one correspondence. So that is the reason I can say that this sigma star, which is set of all binary strings, that is countable. Is this clear? Okay, so remember this sigma star, which is set of all binary strings. This is set of all binary strings is countable. Is countable. Okay, so very simple proof. So like this, you can create a bijection between sigma star comma set of natural numbers. So the cardinality of sigma star, that will be same as cardinality of set of natural number. Okay, so I can say this sigma star, this is countably infinite. This is countably infinite. So this is the idea. I hope you understood this proof. So like this, easily you can prove. This is your proof number 1. You can create a bijection between sigma star and set of natural number. So like this, you can prove. Like this, you can prove that sigma star is countable. Okay. Let's see another proof. We can create another proof also. Okay. So let's see another proof. Proof number 2. Tell me. Give me another proof. Proof number 2. What will be proof number 2? You want to prove sigma star is countable, means set of all finite length binary strings is countable. What is the proof number 2? The proof number 2 is, see, you can create enumeration, right? Yes or no? You can create enumeration. You can create enumeration. You can create enumeration of sigma star. Okay, you can put them in a sequence. You can put them in a sequence. You can create enumeration of sigma star. Okay, all the finite length binary strings, you can put them in a sequence. You can put them in a sequence. Okay, see, in a lexicographic order. This enumeration you can create lengthwise. This enumeration you can create lengthwise in lexicographic order. In lexicographic order. Dictionary order, I can say. I can say dictionary order. Is this clear? Lengthwise in dictionary order. Lengthwise in dictionary order you can put. Okay, so tell me what you will get. Let me know. Lengthwise you can put all these binary strings. This is your sigma star. Sigma star is A or B whole star, because your sigma is A comma B. This is your sigma A comma B. So what you can do? You can create an enumeration. We can create. So remember, we can create enumeration. We can enumerate them. We can create an enumeration of sigma star. Sigma star. Okay. How will you create this enumeration? Let me know. How will you create this enumeration? We can create this enumeration lengthwise in dictionary order. Okay, just go lengthwise. Just go lengthwise in dictionary order. Okay, use the dictionary order. Lengthwise in dictionary order. This is what you do. Okay, so very simple. So first you will put all the 0 length strings. First you will put all the 0 length strings. So first you will put all the 0 length strings. How many 0 length strings are there? How many 0 length strings? Only 1. Okay, then you will put all the 1 length strings. Then you will put all the 1 length strings. 1 length strings. Okay, very simple. Only 2 1 length strings you have. So use the dictionary order. Use the dictionary order. So you can put like this. Then what you can do? You can put all the 2 length strings. You can put all the 2 length strings. Again, put them in the dictionary order, like AA, then AB, then BA, then BB. Yes or no? Is this clear? So these are the 2 length strings. Very simple. Then you put all the 3 length strings. Then you put all the 4 length strings. Okay, then you put all the 5 length strings, and so on. And so on. And you put them in the lexicographic order, means in the dictionary order. So this is your enumeration. Tell me, in this enumeration, can I say every string will appear? Let me know. In this enumeration, can I say every string will appear? Look at this enumeration. In this enumeration, will every string appear? In this enumeration, I am enumerating like this. Will every string appear? Yes. Yes, every string will appear. Yes or no? You can easily notice every string will appear. Tell me where 4 length strings will be appear. Where 4 length strings will appear after 3 length strings. Yes or no? After these, the 4 length strings will appear. Then 5 length strings. Then 6 length strings. Okay, like this. So every string will appear in this enumeration. So this is your enumeration. So this is your enumeration. So because we can create enumeration of sigma star, so sigma star is countable. Yes or no? Okay, since there exists enumeration, we can create an enumeration, right? Okay, since there exists enumeration of sigma star, we can create enumeration of sigma star. So what I can say, so sigma star is what? Tell me. Sigma star is countable. Okay, so sigma star is countable. Very simple. Okay, very easily you can do. Okay, can you give another proof? Proof number 3. Can you give another proof? That is your favorite. That is your using definition number 3. Using definition number 3, right? Okay, using definition 3 of countability. Using definition 3 of countable set. Of countable set. You can use the definition 3 of countable set. Okay, what is definition 3 of countable set? Tell me. What is the definition 3 of countable set? Definition 3 of countable set. This definition, I told you that this definition we found in a research paper, right? Okay, this definition you will not find in the books. Okay, in any standard book, you will not find this definition. This definition you can find in a research paper. We have already seen this. Anyway, definition 3 of countable set. When can I say S is countable? When can I say S is countable? Set S is countable if and only if what you can do. Set S is countable. Set S is countable if and only if what you can do. What you can do to every natural number. To every natural number. If we, okay, if and only if to every natural number we can assign finite set of elements, finite subset. Okay, I can say finite subset of elements, finite subset of elements of S, which covers entire S. Okay, which covers entire S, which covers entire S. Okay, yes or no? Which covers every element of S. I can say which covers every element of S. Element of S. Okay, so remember, if we can do this, if we can assign, if we can do this, means to every natural number, you can assign a finite set of elements of S, which covers every element of S. Then you will say that S is countable. Okay, very simple. So tell me, how will you prove that sigma star is countable? Using definition 3. So this is your set of natural numbers. This is your 1, 2, 3, 4, 5. Okay, and so on. This is your set of natural number. And this is your sigma star. This is your sigma star. Okay, so what you will do? To 1, what you will assign? Tell me. To 1, what you will assign? You will assign all the 1 length strings, right? Yes or no? To 1, you will assign all the 1 length strings. Okay, just assign all the 1 length strings. For example, you can assign this. Also assign epsilon also. Okay, also assign epsilon also. Just assign these 1 length strings. To this 2, what you will assign? You will assign all the 2 length strings. You will assign all the 2 length strings. Just assign all the 2 length strings. To this 3, what you will assign? To this 3, what you will assign? You will assign all the 3 length strings. All the 3 length strings you will assign. Is this a finite set? These 3 length strings. These 3 length strings. Yes, this is a finite. Yes, this is a finite set. Okay, why? Because how many elements are there? How many elements are there in this? How many 3 length strings we have? How many 3 length strings we have? That is 2 power 3. Only 8 3 length strings we have. Yes or no? 2 power 3 elements you have here. So very simple. Okay, similarly, I can say to this 4 also what you will do? You will assign all the 4 length strings. To this 4, you will assign all the 4 length strings. Okay, and you can notice this is also finite set. This is also finite set. In this finite set, you have 2 power 4. That is your 16 elements. Here you have 16 elements. So like this and so on. Okay, and so on. To this 5, you will assign all the 5 length strings. To this 6, you will assign all the 6 length strings and so on. So like this. Does it cover every element of sigma star? Tell me. If we do like this, does it cover every element of sigma star? If we do like this, does it cover every element of sigma star? Yes. Every element of sigma star is covered. Remember, Okay, we have covered every element of sigma star. And can you notice, to every natural number, are we assigning finite set of elements? To every natural number, are we assigning finite set of elements of sigma star? Yes, to every natural number, we are assigning finite set of elements of sigma star. So using definition 3, you can see sigma star is countable. So finally, this is the conclusion. This is very important, that set of all finite length strings is countable. Okay, if your sigma is a comma b, this is the final conclusion, that if your sigma is a comma b, then remember sigma star is countable set. This is countably infinite set. This is countably infinite set. Okay, and what is sigma star? Remember, sigma star is set of all finite length binary strings. This is set of all finite length binary strings. Set of all finite length binary strings. So this is countable. Okay, this set of all finite length binary strings, this is countable. This is countable. And one thing I want to tell you, you can take any sigma, it does not matter. Any sigma you take, you can take any sigma, you can take any alphabet. Remember this point, you can take any alphabet. You don't have to take this a comma b. Okay, see, this is a binary alphabet, right? This is a binary alphabet, but you can take any alphabet, it does not matter. Whatever alphabet you take, sigma star will always be countable. Sigma star will always be countable, means set of all finite length strings, that will always be countable. Is this clear? Whatever sigma you take, for example, if you take this sigma, if your sigma is this, then also sigma star is countable. Then also your sigma star will be countable. Set of all strings, that will be countable. If your sigma is binary, then also sigma star is countable. And if your sigma is, let's assume your sigma is English alphabet, then also sigma star is countable. So whatever sigma you take, so remember, whatever alphabet you take, whatever sigma you take, sigma star is always countable. Is this clear? Let me know. So sigma star is always countable for any alphabet. You can take any alphabet, sigma star is always countable. Okay, for every alphabet, remember, this sigma star is countable. So I can easily say set of all finite length binary strings, that is also countable. So very easy. Now, tell me one thing. Can I say every language is countable? Can I say every language is countable? Yes, every language is countable, right? Every language is countable. Why? Because every language is subset of sigma star. And we know that subset of countable set is countable. Subset of countable set, that is countable. That we already know. If you have a countable set, then subset of countable set, that will always be countable. So remember, every language is countable. Why? Because every language is subset of sigma star. You can see here, every language is subset of sigma star. So whatever language you take, remember. So remember this point, every language L is countable. Every language L is countable. You can take whatever language L you take, that will be countable. For example, if you take L equal to 5, that will be countable. Okay, that will be countable. This is countable because this is finite. If you take L equal to, let's assume this BA, this is a finite language, this is also countable. If you take L equal to ending with A, this is also countable. Okay, if you take L equal to A power n, B power n, okay, n greater than equal to 0, this is also countable. Remember, every language is countable. You can take whatever language you want, that is countable. Why? Because what is the definition of language? See, every language is subset of sigma star, that you already know. Every language L is subset of sigma star, that we already know. This is the definition of language. Okay, whatever language you take, remember this point, whatever language L you take, what will happen? This L will be subset of sigma star. Okay, so, and because this sigma star itself is countable, so I can say this L also will be countable. So this L also will be countable. Okay, because this sigma star is countable, so I can say that this L, automatically this L also will be countable, because subset of sigma star is countable. Okay, subset of countable set is countable. Okay, every language is subset of sigma star. Sigma star is countable, so every language is countable. Okay, so this is the idea. Now, what about set of all languages? What about set of all languages? That is uncountable, right? Yes or no? What about set of all languages? If you take all the languages, set of all languages, this set of all languages, remember, set of all languages, this is uncountable. This is uncountable. Why? What is the reason? Set of all languages is uncountable. What is the reason? Because first of all, what is set of all languages? Tell me. What is set of all languages? Set of all languages is power set of sigma star. Yes or no? That is power set of sigma star. Okay, this is your power set of sigma star. Here you have every subset of sigma star. Okay, this is your every subset of sigma star, means this is your set of all languages, and that is uncountable. That is uncountable. Okay, that is uncountable. So remember, set of all languages, that is uncountable, but every language is countable. So this difference you have to understand. A language and set of all languages. This difference. Is this difference clear? A language and set of all languages. So remember, a language is subset of sigma star. A language, that is subset of sigma star, and set of all languages, that is power set of sigma star. Okay. A language, this is set of sigma, this contains strings. Yes or no? This contains strings. This contains strings. And what this contains? Tell me what this contains. This contains languages. This contains languages. So this is the idea. Okay, so remember this point. So understand the difference between these two. Every language is countable. A language, that is countable because that is set of strings. But set of all languages, that is uncountable. That is uncountable. So this difference you have to understand. So remember, every language is countable, but set of all languages is uncountable. Okay. Can I say every not RE language is countable? If L is not RE, if L is not RE, tell me, if L is not RE language, not recursive enumerable language, if L is not RE language, then can I say L is countable or uncountable? Tell me. If L is not RE language, then what is L? What is L? L will be countable, right? L will be countable because every language is countable. See, it is not RE, that does not matter. L is not RE language, that does not matter. That does not matter because every not RE language is also subset of sigma star. See, this L is also subset of sigma star. Okay, this L is also subset of sigma star, and we know sigma star is countable. Subset of countable is countable. So this L also will be countable because subset of sigma star, that is countable. So remember, if you have not RE language, if L is not RE language, that is also countable. But set of not RE languages, what is that? If I ask you, set of not RE languages, what is that? Set of all not RE languages. Set of all not RE languages, what will be that? Set of all not RE languages. Now I am considering set of all not RE languages. That will be uncountable. Okay, that will be uncountable. So this you have to understand. A particular not RE language, that will be countable. Yes or no? If you take a particular not RE L, if you take a particular not RE language L, that will be what? If you take a particular not RE language L, that will be what? That will be countable. Remember, that will be countable. But set of all not RE languages, if you take set of all not RE languages, if you take set of all not RE languages, if you take set of all not RE languages, that will be uncountable. That is going to be uncountable. Okay, so this difference you have to understand, that a particular not RE language L, that will be countable. But set of all not RE languages, if you take, that will be uncountable. Okay, is this clear? So very simple. So you can see. So remember, every particular language is countable. Yes or no? Every language L is countable. You can easily see here. Every language is countable. So every regular language is countable. Every non-regular language is countable. Every CFL is countable. Every decidable language is countable. Every undecidable language is countable. Every RE language is countable. Every not RE language is countable. Basically, every language is countable because every language is subset of sigma star, and subset of countable set is countable. Okay, so very simple. Now you can easily notice set of all RE languages will be countable. Yes or no? Set of all RE languages, if you take set of all RE languages, that will be countable. But set of all not RE languages, that will be uncountable. Okay, is this clear? So very simple, that set of all RE languages will be countable. See, this is your set of all RE languages. These are your RE languages. So let's assume this is all the languages. This is your all the languages. This is set of all languages. This is set of all languages. What is that? Set of all languages. What is that? Set of all languages. That is your power set of sigma star, right? That is your power set of sigma star. Okay. This is your set of all languages. Now, you can easily notice that this is the set of all languages. Here, some languages are RE. For example, these are the RE languages. Let's assume this is the set of all RE languages. This is RE set. Okay. Here, every language is RE. L1, L2. Here you have this language also. Here you have A power N, B power N also. Here you have WW also. So this is your set of all RE languages. Okay. This is countable. This is countable. Okay. Remember, set of all RE languages, that is countable. But this set of all not RE languages, this is your set of not RE languages. Okay. This area is not RE set. This area is not RE set. This is the not RE set. Okay. And this not RE set, this is uncountable. This not RE set, this not RE set, this not RE set, this is uncountable. Is this clear? So this set of all RE languages, that is countable, but set of all not RE languages, that is uncountable. Similarly, set of all regular languages is countable, but set of all non-regular languages is uncountable. Okay. Set of all regular languages, that is countable, but set of all non-regular languages, that is uncountable. Is this clear? Please tell me. So these are some points you can easily notice. So these are some more results from TOC, from theory of computation, countability results in theory of computation. We have already seen all these proof. Okay. We have already seen all these results, all these proof, everything we have seen. Okay. So let me revise that set of all DFAs is countable. Set of all NFAs is countable. Set of all Turing machines is countable. Set of all context-free grammar is countable. Set of all DPDA is countable. Okay. Set of all grammars is countable. Set of all grammars is countable. Set of all automata is countable. Set of all regular expressions is countable. All these things we have already seen. Okay, so this is just a revision of all the results that we have seen. Countability results in theory of computation. So this is just a revision of that. So remember, set of all grammars, that is countable, because every grammar you can convert into a string. Yes or no? Every grammar you can convert into a binary string. Every automata you can convert into a binary string. Every Turing machine you can convert into a binary string. So the set of all Turing machine, that is also countable. Set of all regular expression, that is also countable. Similarly, set of all programs is also countable, because if you have any program inside your computer, every program is just a binary string. Yes or no? See, you write a program. Let's assume you are writing a very big program, but you can notice inside your computer, that program is just a binary string. So can I say that set of all programs, that is nothing but set of strings? Yes or no? Set of all programs, that is nothing but set of strings. And set of strings is countable. We have already seen set of strings is countable. Similarly, set of all Java programs, that is also countable. Okay. So very easily, you can see this is your question, and I hope you understood everything in this question. So tell me, you understood that set of all strings over sigma, that will be countable. Okay. Please tell me one thing. When I say set of all strings, am I including infinite length strings? When I say set of all strings, am I including infinite length strings? No. Okay. Because by default, string means finite length strings. Okay. So remember this point, that by default, please understand that by default, or I can say in theory of computation, string means finite length strings. So remember this point. By default, when I say string, that automatically means what? String, that automatically means what? That means finite length strings. That automatically means finite length string. Okay, because remember, if I include infinite length string, then this will become uncountable, right? Yes or no? See, if I include infinite length strings, then this will become uncountable. But remember, in theory of computation, or I can say by default, string always has finite length. Okay. So that is the reason this is countable. So this sigma star, this is your sigma star. And we have already seen that sigma star is countable for every sigma. This is countable infinite for every sigma. For any sigma. You can take any sigma whatever you want. It does not matter which sigma you are taking. You can take any sigma you want. This sigma star, that will always be countable. Okay. And set of all languages, that is always uncountable. That is always uncountable for every sigma. Uncountable for every sigma. Remember, this is uncountable for every sigma. Whatever sigma you take, this power set of sigma star, that will be uncountable. Okay, set of all regular languages, that is countable. Set of all regular languages, that is countable. Set of all RE languages, that is also countable. Okay, so very simple. So this is your question. This is the GATE exam question. I hope you understood this question. And in this question, we have done the revision of countability results of in theory of computation. Yes or no? Countability results in theory of computation. This revision also we have seen. I hope you understood this. Okay, so in this question, we have done the complete revision of countability results in theory of computation. Okay, so very simple. Now remember, if you want to study all these results with proof, then you can watch this lecture number 7. Okay, on the Go Classes YouTube channel, you can find this playlist, this countability playlist. You can find this playlist, countability complete playlist. You can notice countability complete playlist. In this playlist, this lecture number 7 you can watch. See here, in this lecture number 7, we have seen countability results in theory of computation. Okay, so this we have seen with proof. With proof we have seen every result. With proof we have seen a lot of results. We have seen a lot of results with proof we have seen. Okay, so if you want to understand, then you can watch this lecture number 7. Okay, let's move on now. Now let's see this GATE exam question. GATE Computer Science 2014 question. Let's solve it. Sigma is finite non-empty alphabet. This sigma is finite non-empty alphabet. This is given to you. Okay. 2 power sigma star, that is power set of sigma star. Okay. What is sigma star? Tell me. Whatever sigma you take, then what will be sigma star? Whatever sigma you take, sigma star will be set of strings, set of all strings. That is your set of all strings. Very good. And this set of all strings, this is countable, right? Whatever sigma you take, this is always countable. Whatever sigma you take, this sigma star is always countable. Okay. So remember, for every sigma, so this is important, that for every sigma, you can take any sigma, this sigma star is always countable. This sigma star, this is always countable. You can take any sigma. Okay, for every sigma, whatever sigma you take, for example, you can take this sigma, you can take binary sigma. Okay, binary alphabet you can take, or you can take any alphabet. For example, English alphabet you can take. But the point is, for every sigma, this sigma star, this is always countable. Okay, this is always countable. Sigma star means set of all strings. This is always countable. Okay, so very simple. This is the point, that sigma star is countable. What about power set of sigma star? Okay, 2 power sigma star, this is your power set of sigma star. What about power set of sigma star? This will be uncountable. This will be uncountable. Okay, this power set of sigma star. What is power set of sigma star actually? What is power set of sigma star? This is set of all languages. Yes or no? This is set of all languages. So remember, set of all languages, that is uncountable. Okay, and you can easily prove it. See, this is not a hard thing. You know that sigma star is uncountable. Sigma star, that is countably infinite. We know that sigma star is countably infinite. This we already know. Okay, sigma star, this is set of all strings. This is countably infinite. Okay, this is countably infinite. So this is your sigma star. Now you tell me, we know from Rice theorem what we know? Sorry, from Cantor's theorem. From Cantor's theorem, what we know? From Cantor's theorem. What Cantor's theorem says? See, Cantor's theorem says that if S is infinite set, then power set of S will always be uncountable. Yes or no? See, we already know this. If you remember, if S is infinite set, if S is any infinite set, you can take any infinite set. Remember, you can take any infinite set. If S is infinite set, then we already know that power set of S is always uncountable. is always uncountable. Agree? Yes or no? Yes or no? Tell me. So this is what we have seen. This we have seen in the Cantor's theorem. So from Cantor's theorem, you can easily see that if S is any infinite set, then power set of S will always be uncountable. That will always be uncountable. Okay. So very simple point. This is what I am saying. I am saying that if S is any infinite set, it should be infinite. Okay. If S is any infinite set, it does not matter. It is countable, uncountable. It does not matter. If this is any infinite set, then remember this point, that power set of S, that is always uncountable. We have already seen this in the Cantor's theorem. With proof we have seen. Okay, with proof we have already seen in Cantor's theorem. So this result we have already seen. Now you can easily see. Now you can easily see. Now you can easily see sigma star is infinite, right? Yes or no? Sigma star, set of all strings, this is infinite, correct? Sigma star, this is an infinite language, set of all strings, this is infinite. Agree with me? This is countably infinite, but this is infinite set. Okay, this is infinite set. This is your infinite language. This is an infinite language. So tell me, if this is an infinite set, then what you can say about power set of sigma star? You can see, if S is infinite set, then power set is always uncountable. Okay, so very simple. So this power set of sigma star, this will be uncountable. This will be uncountable. Okay. And you can easily see from here, I can also say from here, what I can say that from this Cantor's theorem, remember, from this Cantor's theorem, I can also say one thing. What? That infinite power set can never be countable. Yes or no? From here, you can easily say that. So an infinite power set, if you have a power set which is infinite, an infinite power set is never countable. Yes or no? Is never countable. Is this clear? See, very simple point. Because if you have an infinite power set, then that will always be uncountable. So an infinite power set is always uncountable, is never countable, or I can say is always uncountable. Okay, I can also say is always uncountable. Is always uncountable. So very simple point. So easily you can see for this question that sigma star will be countable, but power set of sigma star will be uncountable. So what will be the answer? The question is asking which is true. So the answer will be option C. Option C will be the answer. Okay, so this is a very simple question. The question is only asking sigma star and 2 power sigma star. Sigma star is set of all strings. Sigma star, that is set of all strings. That is countable. Infinite. And 2 power sigma star, that is your power set of sigma star. That is set of all languages. And that is uncountable. Okay, so very easily you can see. So this question we have done. Now let's solve this question. This is GATE 2019 question. So let's solve it. The question is saying, consider the following set. The set of all recursive enumerable languages. What that? Set of all RE languages. That is countable, right? Yes or no? Set of all RE languages is countable. Set of all RE languages, that is countable. That we already know. Set of all RE languages, that is countable. Okay. What about set of all valid C programs? See, set of all programs is countable. Set of all programs, that is countable. What about set of all languages? Set of all languages, this is your power set of sigma star. And this is uncountable. Set of all languages, that is uncountable. And what about set of all non-regular languages? That is also uncountable. Set of all non-regular languages, that is also uncountable. Okay. So the question is asking which set is uncountable? The answer will be S3, S4. The answer will be option B. Option B will be the answer. Okay. So this is your answer. You can see. Is this clear? Please tell me. So very simple. Now, let me just tell you that set of all programs is actually countable. Yes or no? Set of all programs, whatever program you can write, set of all programs is countable. Set of all programs. You can take any program, set of all programs is countable. Why? Tell me why. What is the reason? Let me know why. What is the reason? Set of all programs is countable. Why? Just think about it. That any program you take, that is just a string inside your computer, right? Okay. If you take any program, if I give you any program, you can have a very big program. If you take any program, let's assume this is any program P. Let's assume this is any program P. You can take any program P. Tell me inside your computer how this program will look like. Inside your computer, you are writing a program. Let's assume you are writing a C program, a very nice C program you are writing. Let's assume this is a very long program. Okay, let's assume this has 1 trillion lines of program. Okay, this is 1 trillion lines of program. Now, but inside your computer, this program is just a string. Yes or no? Inside your program, this is just a binary string. Inside your computer, this is just a binary string. This is just a binary string inside your computer. Very simple. Agree with me? So remember, you have this program. Inside your computer, this program is just a binary string. So when I say set of all programs, what is that? When I say set of all programs, that automatically means set of strings. Set of finite length strings, right? Because of course it will be a finite length string. When you convert your program to a string, then that will be a finite length string. Okay, so this is just a set of finite length strings, and set of finite length strings, that is countable. Set of finite length strings, that is countable. Okay, so very simple point, that set of all programs is countable. So we have seen option S2. Option S2 we have seen. Set of all syntactically valid C program. Even if it is syntactically invalid, then also it is countable, right? Yes or no? See, if you consider all the C program, forget about syntactically valid. If you take all the C program, if you take all the programs, all the Java program, all the C program, all the Python program, if you take all the programs, if you consider all the set of all programs, that is also countable. Because remember, whatever program you take inside your computer, this is just a string. Inside your computer, that is just a string of finite length. Yes or no? That is just a string of a finite length. This is just a string. This is just a binary string of finite length inside your computer. So when I say set of all programs, that automatically means set of finite length strings, and that is countable. So very simple. This is your statement S2. Okay. Now let's see statement S4, S3. Let's see statement S4, S3. See, this we already know that whatever sigma you take. See, this we already know. Whatever sigma you take, you already know that sigma star, that will be countable. You already know this. Sigma star will be countable. And we already know that power set of sigma star means set of all languages, that will be uncountable. If you consider set of all languages, that will be uncountable. Okay. We also know set of all regular languages is what? Tell me. Set of all regular languages. What is that? Set of all regular languages. Tell me. Set of all regular languages. What about that? See, set of all languages is uncountable. Set of all languages, that will be uncountable if you consider all languages. But if I consider set of all regular languages, that is countable. We have already seen in our lectures. Okay. So this is countable, right? Now you tell me about set of all non-regular languages. See, very simple point. This is your set of all languages. This is the set of all languages. This is the set of all languages. I can call it power set of sigma star. This is your power set of sigma star. And we already know that this is uncountable. Okay, this set of all languages, this is uncountable. Okay, this is uncountable. Now, here you have some regular languages, correct? Okay, these are the regular languages. Let's assume this is the regular set. This is the regular set. Means here you have regular languages. Okay, like this language you have, this is a regular language. Okay, for example, this is a regular language. Okay, and so on, and so on. So these are the regular languages. Now, this is countable. This is countable. This is countable. So tell me about Set of all non-regular languages. Set of all non-regular languages. What about that? Tell me. What about that? Now you tell me about non-regular set. This set of all non-regular languages. This set means this is a non-regular set. This is non-regular set. What about this non-regular set? See, this complete set of all languages is uncountable. If you consider set of all languages, that is uncountable. Set of regular languages is countable. So what should be this remaining set of all non-regular languages? So what should be this set of all non-regular languages? This will be uncountable, right? Yes or no? This will be uncountable. This will be uncountable because remember, uncountable minus uncountable is always, see, uncountable minus countable. This we have seen. Uncountable minus countable. Uncountable minus countable. That is uncountable. That is uncountable. Yes or no? So if you notice this non-regular set, if you look at this non-regular set, can I say set of all non-regular languages? That is set of all languages minus regular set. Minus regular set, right? Yes or no? Okay. So you can see this is uncountable. Set of all languages. Set of all languages. This is uncountable. And this set of regular languages, this is countable. This is countable. So automatically what this will become? Automatically what this will become? Tell me. Uncountable minus countable is uncountable, right? Uncountable minus countable, that is uncountable. Okay. So this is your answer. So set of all non-regular languages, that will be uncountable. So we have seen this. Set of all non-regular languages, that will be uncountable. Okay. And set of all regular languages, that will be countable. Set of all languages, that will be uncountable. Okay. Set of all programs, countable. Set of all RE languages, countable. So this is your question, and we have seen very easily you can solve this question. So the question is asking which is uncountable. The answer will be option B. Okay. So if you want to understand all these concepts with proof, then you can watch this lecture. You can watch. Okay. You can see Countability lecture 7, Countability results in theory of computation. Okay. So in this, we have already seen all these questions, all of them with proof we have seen. So you can watch this lecture, lecture number 7, in this Countability playlist on the Go Classes YouTube channel. Okay. So you can just watch it if you did not watch. Okay. This is your Countability complete playlist. Here you have all the lectures. Okay. You can watch it. This lecture number 7. Here we have Countability results in theory of computation. Okay. With proof. Now let's move on. Let's solve this question. This is GATE Computer Science 1994 question. GATE Computer Science 1994 question. Every subset of countable set is countable. This we already know, right? Yes or no? Every subset of countable set is countable. This we already know. Okay. So this statement is true. This statement is true. See, you can state whether the statement is true or false with reason. What reason you can give? See, this statement is true. This statement is true. Every subset of countable set is countable. This statement is true. And what is the reason that you will give? What is the reason that you will give? Tell me. What is the reason that you will give? Let me know. What will be the reason that you will give? See, the reason. Let me give you the reason. You tell me one thing. We know this. You tell me one thing. We know this, that if there exists an injective function, see, if I can give you an injective function, just tell me a very simple question I'm asking. Okay. If I can give you an injective function, if there exists an injective function from set S to a countable set, A, then what you can say about S? Think about it and tell me. If there exists an injective function, this we have already seen, right? If there exists an injective function, from set S to a countable set, then what you can say? Then I can say cardinality of S is less than equal to cardinality of A. Okay. And remember, this is countable. We are saying this is countable. This is countable. So what will be this set S? So what will be this set as? Tell me, what will be this set as? That also will be countable, right? Yes or no? That also will be countable. Is this clear what I'm saying? Please tell me. See, very simple point. If there exists an injective function from set S to a countable set, then S is countable. Then S is countable, right? Okay, then S is countable. Now, a very simple question I'm asking, that take any countable set. Okay, take any countable set. Take any countable set. Take any countable set S. Or you can take any countable set A. Any countable set you can take. Take any countable set A. Let's assume these are the elements A1, A2, A3, and so on. Let's assume this is your countable set. This is any countable set. Okay, this can be finite or this can be countably infinite, remember. So let's assume this is any countable set. Now, consider any subset of A. Consider any subset of A. Consider any subset of A. Just consider any subset of A. Whatever subset you want, you can consider. Just consider any subset of A. For example, let's consider this subset, like A3, A7, A9. Okay, some subsets. Are you getting my point? Okay, let's consider some subset. Any subset you can take. You can take any subset you want. Is this clear? So consider any subset of A. So remember, this is subset of countable set, right? This is subset of A. This is subset of A. Okay, and remember, A is countable set. Remember, A is countable set. You know this A is countable set. Now, can you give me injective function from S to A? Can we create injective function from S to A? Can we create? Is there exist injective function from S to A? Tell me. Can we create injective function? Injective function from S to A. From S to A. Tell me. Can you create an injective function from S to A? Let me know. First of all, you tell me, if we can create, then what will happen? If we can create, then what will happen? Just tell me. If we can create from S to A, if we can create injective function, then what will happen? Then I can say S is countable, right? Yes or no? Then I can say S is countable. Agree with me? If I can create an injective function, then S will be countable. Please tell me, agree or not? Okay, because if we can create, notice, if we can create, then what it will mean? Then what it will mean? Then it will mean that cardinality of S is less than equal to cardinality of A. Okay? Which means S is countable. Okay? So can you create injective function from S to A? From S to A, can you create injective function? This is your set A. See, this is the set A. Here you have elements A1, A2, A3, A4, and so on. This is your set A. This is your subset. This is your subset S. This is your subset S. It has A3, A7, A9, something like that. A3, A7, A9, let's assume A10, and so on. So can you give me injective function? Anyone want to give me injective function? Can you give me injective function from S to A? Remember, S is subset of A. Remember, S is subset of A. You can notice S is subset of A. You can notice S is subset of A. So can you give me injective function from S to A? See, very simple. Fx equal to X. Just consider this. Fx equal to X. Yes or no? Just consider Fx equal to X. Very good. Very good. Very good. Very good. Okay, so you can see A3 mapping to A3, A7 mapping to A7, A9 mapping to A9, A9 mapping to A9, A10 mapping to A10. Yes or no? Is this clear? Please tell me. Okay, and so on. So can you notice, if you do this, this will be injective, right? This will be an injective function. This is an injective function. Because there exists an injective function, so what I can say? Because there exists an injective function, so what I can say? Because there exists an injective function, so I can say S is a countable. Okay, yes or no? So S is countable. So this is the reason. Is this clear? Please tell me, let me know. See, this is very intuitive, that subset of countable set is countable. Any subset, if you take subset of countable set, that is countable. Subset of countable set is countable. And this is very intuitive if you notice. Okay, this is very intuitive that if you take a subset of countable set, that will be countable. This is quite intuitive. Okay, so first of all, remember, this result is actually intuitive. You can intuitively see this. Okay, you can intuitively understand that if you take a subset of countable set, that definitely will be countable. So intuitively you can understand. But if you want a formal proof, then what you can do? If you want a formal proof, what you can do? If you want a formal proof, like someone asks you, what is the formal proof? Then the formal proof is very simple. Formal proof is very simple. Okay, because there exists a injection. Yes or no? Because there exists an injection. So you can see if S is subset of A, then there exists an injection. Then there exists an injective function. You can create an injection. Then there exists an injection F, injective function F from S to A. Okay, by this rule, Fx equal to X. By this rule. So I can say cardinality of S will be less than equal to cardinality of A. This will always happen. Okay, so this will always happen. Cardinality of S that is less than equal to cardinality of A. Now, since this A is countable, since this A is countable, so S is also countable. So S will also be countable because cardinality of S is less than equal to cardinality of A. Yes or no? Cardinality of S that is less than equal to cardinality of A. So if A is countable, then S also will be countable. Okay, so this is how you can prove it. Is this understood? Please tell me. So remember, very simple, that subset of countable set is countable. Subset of countable set is countable. Okay, subset of countable set that is countable. Very easily you can solve it. Okay. Let's solve this question. This is TIFR 2022 question based on countability. So let's solve this. The question, what this question is saying, TIFR 2022, this question is saying that a binary string is a sequence of 0, 1. Okay, this is the first line. You can see a binary string is sequence of 0, 1. Now the question is saying a binary string is finite if the sequence is finite. Otherwise it is infinite. Okay, for example, this is a finite length binary string. This is a finite length binary string. Which of the following is true about the set of all finite length binary strings and set of all infinite length binary strings? Okay, so tell me, set of all finite length binary strings, that is countable, right? Yes or no? Set of all finite length binary strings, that is countable. But set of all infinite length binary strings, that is uncountable. So the answer will be option A. The answer will be option A. Is this clear? See, very simple question. Very simple question. If you take this sigma, means A comma B. Okay. Now, if you consider set of all finite length binary strings, if you consider set of all finite length binary strings, if you consider this set of all finite length binary strings, then that is what? Set of all finite length binary strings. I am considering set of all finite length binary strings. That is what? That is your sigma star, right? Yes or no? That is your sigma star. Sigma star means set of all finite length binary strings. This is your sigma star. And we know that sigma star is countable. We know sigma star, that is countable. Okay, sigma star, that is countable. Okay, your alphabet is 0, 1. This is your alphabet 0, 1. And this sigma star is countable. Can you prove it? Can you prove it? Set of all finite length binary strings is countable. Set of all finite length binary strings. This is countable. Can you prove it? What is the proof? What is the proof? The proof is you can create a bijection between this sigma star and set of natural number. Yes or no? The proof is this. Bijection exists. Bijection exists between sigma star and set of natural numbers. Okay, sigma star and set of natural numbers. Bijection exists. What is that bijection? Tell me. What is that bijection? Let me know. Let me know. What is that bijection? So remember, sigma star is set of all finite length binary strings. This is set of all finite length. This is set of all finite length binary strings. Okay, this is set of all finite length binary strings. Now I'm saying bijection exists. Okay, consider this f from sigma star to set of natural number. From sigma star to natural number, what I do from sigma star to natural number. Remember, this is your sigma star. This is your sigma star. In sigma star, you have this is a finite length binary string. This is a finite length binary string. So you have all the finite length binary strings. You have all the finite length binary strings. You have all the finite length binary strings. And this is your set of natural numbers. This is the set of natural numbers. Here you have set of natural numbers like 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. So can you create a bijection? Can you create a bijection? One-to-one correspondence can you create? Can you create one-to-one correspondence? So what will be FW? Can I create I want one-to-one correspondence. Remember, I want one-to-one correspondence. I want one-to-one correspondence. This is what I want. Is this clear? I want one-to-one correspondence. This correspondence I want, please understand. I want this correspondence, remember. I want a one-to-one correspondence. This type of one-to-one correspondence I want. Okay, between set of all finite length binary strings and set of natural numbers. I want a one-to-one correspondence. This is what I want. Okay, so can you give me a one-to-one correspondence? Yes, very easily you can give. FW will be decimal value of 1W. Okay, just do decimal value of 1W. Okay, decimal value of 1W. Just put 1 before it. Okay, means if you want to find the image of 0, 1, then put 1 before it. So image of 0, 1 will be the decimal value of 101. Yes or no? So this is what I'm saying. What you do? FW, that is decimal value of 1W. That is decimal value of 1W. Okay. So if you want to find the F epsilon, that will be decimal value of 1 epsilon. That will be decimal value of 1 epsilon. And what is 1 epsilon? The decimal value of 1 epsilon. That will be 1. The decimal value of 1 epsilon, that will be 1, right? Yes or no? So similarly, tell me what the decimal value, what the image of 0, 1, 1. Tell me what will be the image of 0, 1, 1. Let me know. What will be the image of 0, 1, 1? See, image of W is decimal value of 1W. Image of W is decimal value of 1W. 1W. Just put 1. So the image of 0, 1, 1 will be decimal value of 1, 0, 1, 1. And what is that? 1, 0, 1, 1. That is 11. So the image will be 11. Yes or no? So very simple point. If you do this, image of W is decimal value of 1W. Now, if you do this, you will get this. The image of epsilon will be 1. Image of 0 will be 2. Image of 1 will be 1. Image of 1 will be 3. Image of 00 will be 4. Because what will be image of 00? Tell me. What will be image of 00? FW is decimal value of 1W. FW, that is decimal value of 1W. So tell me, what will be what will be F00? That will be decimal value of 100, right? And that is 4. That is 4. So very easily you can see. Okay, so this is what we are saying. So the decimal value of the image of what will be the image of 0, 1? That will be 5. Image of 1, 0, this. Okay, so you can easily notice. You can easily notice. Easily. So that's it. So there exists a bijection, right? Yes or no? There exists a bijection. Agree with me? Okay, so this F, you can notice this is a bijective mapping. This is a bijective mapping. This is a bijective mapping from set of all finite length binary strings to set of natural numbers. This is a bijective mapping. So what I can say? So cardinality of sigma star, that is same as cardinality of natural numbers. Yes or no? So cardinality of sigma star, that is same as cardinality of natural numbers. So sigma star is countable. So sigma star is countable. So this is the proof. Okay. So I can say set of all finite length binary strings will be countable. Is this clear? Because there exists a bijective mapping. Because we can create a bijection. One-to-one correspondence. Okay. So remember this point. So set of all finite length binary strings sigma star is countable. That is countable. Okay, so very simple, because there exists a bijection. So very simple. Now this we have seen. What about set of all infinite length binary strings? What about that? Tell me, what about set of all infinite length binary strings? Infinite length. I want set of all infinite length binary strings. Set of all infinite length binary strings. What about that? Set of all infinite length binary strings. This will be uncountable. Okay, this will be uncountable. Can you prove it? This will be uncountable. Can you prove it? Tell me. Can you prove it? We can prove it using Cantor's diagonalization proof. Yes or no? We can easily prove it. Can prove it using Cantor's diagonalization proof. Okay, Cantor's diagonalization proof. Cantor's diagonalization argument. Okay, you can easily prove it using Cantor's diagonalization argument. Okay, so tell me, how will you prove it? Using Cantor's diagonalization argument, how will you prove that set of all infinite length strings that is uncountable? That is uncountable. See, very simple. All you have to do, just prove that there is no bijection between this set and set of natural numbers. Okay, see what we will do. This is your set of all infinite length binary strings. Okay, consider this. Let's call it set S. This is set of all infinite length binary strings. Correct? Okay, see, let's prove it. Infinite length binary strings. This is your set, binary strings. Set of all infinite length binary strings. Remember, in this set, do we have this string? Tell me. In this set, do we have this string? No, we don't have this string, because this is set of all infinite length binary strings. Okay, is this clear? So this is your set. Now, what to do now? See, we can prove that S is uncountable. This is what we want to prove. We want to prove that S is uncountable. This S is uncountable. How will you prove it? That S is uncountable? You can prove it by contradiction. Okay, prove by contradiction. You can easily prove it by contradiction. Okay, so what you can do? You can assume S is countable. Okay, just assume. I'm assuming S is countable. Is this clear? Remember, S is already infinite. That you already know. Okay, how many infinite length binary strings you can create? How many infinite length binary strings you can create? Tell me. How many infinite length binary strings? How many you can create? Infinite, yes or no? So S is already infinite. That we already know. Okay, that is not a problem. Okay, so assume that S is countably infinite. Just assume this. Okay, assume S is countable. This is what we are assuming. We are assuming that S is countable. Okay, so if you assume that S is countable, so what should happen? Tell me. If you assume S is countable infinite, so what should happen? So there must exist a bijection. So there exists a bijection between S comma N. Yes or no? I can say there exists a bijection from set of natural numbers to this set. Okay, there exists a bijection. Now what you do? Now you take a random bijection. So take a random bijection. So this is what you do. Okay, because remember, if you assume that this S is countable, you already know S is infinite. See, there is nothing here. This S is infinite because, see, your set S, that is set of all infinite length binary strings. Infinite length binary strings. Tell me how many such strings I can create. First of all, you understand infinite length binary strings. So in your set, what you have? Tell me. This is your set S. In your set, what you have? You have infinite length binary strings. For example, all zeros. For example, this string belongs to S. Is this clear? Also, you can easily notice, for example, 0, 1, 0, 1, 0, 1, 0, 1, and so on. This also belongs to S. For example, all ones. This also belongs to S. Okay, for example, maybe 0, 1, 1, 0, 1, 1, 0, 1, 1, and so on. This also belongs to S. And some random string. Okay, some random string which goes infinite, that also belongs to S. So this is what I'm saying. So tell me, this S, this is an infinite set, right? Yes or no? Agree with me? This is an infinite set because you can create infinite number of strings you can create. Infinite number of infinite length binary strings you can create. Okay, so this set S, this is infinite set because you can create infinite number of infinite length binary strings. Okay, now if you assume that this is countable, for contradiction, if you assume that S is countable, then there exists a bijection from N to S. So what you do? So take a arbitrary bijection. This is what you do. So take arbitrary bijection F. Okay, remember, take arbitrary random bijection F. From where to where? From N to S. Okay, take arbitrary bijection F. So let me take this bijection F. What I'm doing, see, notice. So let me take this bijection F. From, remember, from N, this is your set of natural number. 1, 2, 3, 4, 5, 6, and so on. Okay, so you take a arbitrary bijection. So let's assume this is your set. This is the set S. This is the set. This is the set S. Okay, now give me, what should I map to 1? I'm taking, remember, I'm taking an arbitrary bijection. From N to S, I'm taking an arbitrary bijection. Okay, I'm taking arbitrary bijection. So tell me, this one will map to someone, yes or no? This one will map to some element of S. Let's assume this is mapping to this element. See, 1 will map to some element of S. So let's assume this is mapping to this element. Okay, this 2 will map to some element. Let's assume 2 is mapping to this element. Okay, this 3 will map to some element. Let's assume 3 is mapping to this element. Okay, this 4 will map to some element. Let's assume 4 is mapping to this element. Okay, this 5 will map to some element. I'm taking random elements. I'm taking like random elements I'm taking. Okay, this 6 will map to some element. So let's assume this is mapping to this element. Okay, some random elements I'm taking, and so on. So I'm taking an arbitrary bijection. Okay, because I'm assuming there is a bijection. So I'm taking an arbitrary bijection. Okay, so take arbitrary bijection. This arbitrary bijection I have taken. Now what we will do? Now after that, what we will do? Tell me. Now after that, what we will do? Now tell me. Now, if this is a bijection, should it cover every element of S? Tell me. Now, if F is a bijection, it should be a surjection also. If F is a bijection, so every element of S must be covered or not? So every element of S must have a pre-image. Agree? Or I can say that every element of S must be covered. Or I can say every element of S must be covered. Every element of S must be covered. Every element of S that must be covered. That must be covered by F. Okay, yes or no? Very simple. If F is a bijection, then every element of S must be covered. Okay, but what we can do? You are saying that if F is bijection, then every element of S must be covered. Then, but what we can do? But we can create an element which is not covered. But whatever F you take, see this, whatever F you take, whatever F you create, you can create whatever F you create. Is this clear? Whatever F you create, we can find some element. We can find some element X belonging to this set S. Is this clear? We can find some element, let's call it D. We can find some element D belonging to S. Some element we can find which is not covered. Yes or no? Okay, whatever F you take, whatever F you create, we can find some element D belonging to S which is not covered by F. Which is not covered by F. Okay, so how will you find it? So tell me, in this function, how will you find it? Okay, see, This f we have taken. So we have taken this arbitrary f. We have taken this arbitrary f from n to s. Okay. Now what is my target? Now my target is to find some element. I can find some element. See, whatever f you create, I can find some element I can find which is not covered by f. Which is not covered by f. How will I find? Tell me. How will I find? This element d I can find. How will I find? Very simple. See, in my element, I am finding element which belongs to s. I am finding element which belongs to s. Remember, this element I am finding which belongs to s and which is not covered here. Which is not covered here means this element will be different from this element. Remember, my element d, it will be different from this element, different from this, different from this. So it will be different from every element. My element d will be different from this, 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 different from this. Okay, different from every element in this, different from every element in this, different from every element in this. So how to create? Very simple. Okay, just see what will be the first symbol in my string. I am creating an infinite length string. I am creating infinite length string. I am creating infinite length string. I am creating which belongs to s. Okay, so what will be the first symbol in my string? Very simple. See. Here you have 0, right? Here you have 0. Okay, so in my string, the first symbol will be 1. Okay, here you have 0. So in my string, the first symbol will be 1. Now you tell me one thing. Whatever I create, now tell me one thing. Whatever I create, can I guarantee that my string d will be different from this string? Whatever I put here. See, now whatever I put. First symbol is 1. First symbol is 1. Now whatever I put, can I say my string d, that is different from this string? Yes, of course. Okay. Because remember, my first symbol is 1. Now whatever I put here, my string d will be different from this string because of first position. Because of first position. Okay. Now what will be the second position in my string? See, second position. For second position, what I will do? I will look at this mapping. See, here you can notice this is 1, right? So in my element d, in my string d, the second position will be 0. Okay. Now can you notice one thing? Whatever I put, my second position is 0. My second position is 0. Now whatever I create, whatever element d I can create, that will be different from this string because of second position. Because of second position. Okay. Now what will be my third position? See, for third position, I can do this. Here you have 1. So in my string, the third position will be 0. Now you can notice whatever string I create, whatever element d I create, that will be different from this string because of third position. So this is the idea. I hope you understood the idea. Now you can notice what will be my next position. See, for next position, you can see this is 0. So my next position will be 1. Okay. What will be the next position? See, for the next position, this is 1. So my next position will be 0. Is this clear? Next, you can see that. Next, you can see here for the next position, this is 1. So my next position will be 0. And so on. Dot. Okay, it will keep going on. Yes or no? Dot. It will keep going on. It will keep going on. And so on. I will keep going on. Remember this point. I will keep going on like this. Okay. Now tell me one thing. Can you notice this string that I will get? Can I guarantee this will be infinite length string? Can you guarantee this will be infinite length string? Can you guarantee? Can you guarantee this string d I am creating? This string d I am creating, this will be infinite length string? Yes, of course. Why? Can you guarantee this string d that I am creating, this will be infinite length string? Yes, because I will keep doing like this okay, I will keep doing like this. See, I will keep doing like this. I will keep doing like this. So this will be infinite length string. So I can say, so this d belongs to s. Yes or no? So remember, this d belongs to s. But is it covered? This d belongs to s, but is it covered by this f? By this mapping f? Is this covered? Is this covered by this mapping f? So remember, d belongs to s, but d is not covered. But this d is not covered by f. This d is not covered by f. Okay, by this f. This d is not covered by this f. So what I can say, because this D is not covered by this F, so what I can say, so this F is not a bijection. So I can say this F is not a bijection. Okay, because this element is not covered. This element that I created this element, this is not covered by F. So this F is not a bijection. Okay, and remember, F was arbitrary. If you remember, this F was arbitrary mapping. This was arbitrary mapping. This F was arbitrary mapping. Okay, so I can say that there is no bijective mapping. Okay, yes or no? So I can say, so no bijection exists. So I can say no bijection exists from set of natural number to this set S. So what I can say, so contradiction, we got a contradiction, right? So contradiction we got. So contradiction we got. So we got a contradiction. So our assumption was wrong. So our assumption was wrong. So our assumption was wrong. And what was our assumption? Tell me. So our assumption was wrong. What was our assumption? Tell me. Our assumption was wrong. So I can say S is uncountable. Our assumption was wrong. Our assumption was S is countable. Yes or no? We made an assumption. We made one assumption that S is countable. This assumption we made. This assumption we were making that S is countable. This assumption we were making, but we got a contradiction. So our assumption is wrong. So S is uncountable. Our assumption is wrong. So S is uncountable. Okay, is this clear? Very simple. So this is the proof that S is uncountable. Okay, because remember, whatever F you will create, see, whatever F you will create, whatever mapping you will create, I can find some element which you did not cover. I can find some element which you did not cover. Okay, I can find some element which you did not cover. So what I can say? So I can say that no bijection exists. So no bijection exists from N to S. From N to S. Okay, no bijection exists. So because no bijection exists, so I can say S is uncountable. Okay, S is uncountable. Very simple. And what this proof is called? This proof that we have seen, in this proof, did you notice what this proof is called? This proof is called Cantor's diagonalization proof. Because what we are doing here, see, we are going diagonally. Here you have 0, so I will put 1. Okay, here you have 1, so I will put 0. Here you have 1, so I will put 0. Here you have 0, I will put 1. Here you have 1, I will put 0. Here you have 1, I will put 0. Okay, so can you notice that? Okay, can you notice that? We are going diagonally. Yes or no? This diagonally, we are going diagonally. Okay, like this. Like this. Okay, like this we are going diagonally. Okay, this is a diagonal. This is the diagonal. This is the diagonal. So remember, this proof is called Cantor's diagonalization proof. Okay, so this previous proof is called Cantor's diagonalization proof. This previous proof is called Cantor's diagonalization proof. Cantor's diagonalization proof. Okay, so this is the simple idea. So this proof is called, this previous proof, that is called Cantor's diagonalization proof. Okay, because we are creating this element D. This element D we are creating diagonally. Okay, we are creating diagonally. So that is the reason this is called Cantor's diagonalization proof. But anyway, the point is, set of all infinite length binary strings, that is uncountable. This is the simple point. Set of all infinite length binary strings, set of all infinite length binary strings, that is uncountable. And this is your TIFR exam question. So the answer will be what? Answer will be option A. Yes or no? Set of all finite length binary strings, that is countable. Set of all infinite length binary strings, that is uncountable. Okay, is this clear? So your answer will be option A. Option A. Clear? Please tell me. Let me know. Is this clear? Tell me one variation. If your sigma is A, if you have only sigma is unary alphabet, now tell me, what about set of all infinite length binary strings, infinite length strings? If you have only one symbol, now tell me about set of all infinite length strings, over A, over A. Okay, so tell me, let me know. If your sigma is unary, now set of all infinite length strings, tell me, what about this? Set of all infinite length strings, let me know. Only one string you can create, right? Yes or no? Only one string you can create, correct? Yes or no? Tell me. Only one string you can create. Agree? You can create only one string. See, only one string you can create. There is only one string possible. There is only one string possible, right? Because you have unary alphabet. Your alphabet is unary alphabet. You only have one symbol. Now, how many infinite length strings you can create? Tell me. How many infinite length strings you can create? Tell me. Please tell me. How many infinite length strings you can create? Only one string you can create. Yes or no? This is the only string. This is the only string that you can create. Is this clear? Please tell me. This is the only string. Only one string we can create. Only one string possible. You can only create one string. Is this clear? Only one string is can be created. So yes, this will be only, this is a singleton set. Yes or no? So this is a finite set. So this is countable. Is this clear? So this is just a small point, but I hope you understood this. Okay. See, this is just a small point, but you should understand that you can only create one string. You can only create one string. Only one string you can create, because you want to create infinite length string over A. Only one string you can create. Is this clear? Please tell me. So this will be your singleton set. This will be your singleton set. Only one element will be there. So this is just a small point I wanted to tell you. Is this clear? Let me know. Please tell me, is this clear? So remember, set of all infinite length binary strings. Set of all infinite length binary strings is uncountable. Set of all infinite length binary strings is uncountable. Why? Because you can create uncountably many. Is this clear? Set of all infinite length binary strings is uncountable. Binary strings, that is uncountable. Why? Because you can create infinitely many strings you can create. Infinitely, I can say uncountably many strings you can create. Okay. So let's move on now. Let's solve this question. This is TIFR Computer Science 2014 question. And we are only considering the option number A. In this option A, the question is asking, is this countable, uncountable? What is this? So let's see this. This is TIFR 2014 question. Let's focus on the option A. Option A is asking, n star is countable or uncountable? First of all, what is n star? Read the question and tell me what is n star. Read the question and tell me what is n star. Tell me what is n star. See, n star is, you can notice n star is finite sequences of natural numbers. N star is set of finite sequences of natural numbers. Set of finite sequences of natural numbers. Natural numbers. Is this clear? Let me know. So this is your n star. And then we are doing something. See, this is just a relation defined on n star. Okay, remember, this is just a relation defined on n star. This does not have anything to do with the elements. This is just a relation. Some relation is defined. Because you can see in this question, some relation is defined. So please understand, this is just a relation defined. Please understand, this is just a relation defined on n star. This is just a relation defined on n star. We don't care about it. Yes or no? This is just a relation defined on n star. Is this clear? We only focus on n star. So just focus on n star. Forget about everything else. Forget about everything else. Just focus on n star. Now you tell me, is this true or false? Let me know. Did you understand what is n star? N star is set of all finite sequences of natural numbers. Finite sequences of natural numbers. Okay. What is n star? Tell me. N star will be countable. Yes, this is false because n star will be countable. Can you prove it? Can you prove it that n star will be countable? N star actually will be countable. Can you prove it? Yes, we can easily prove. See what you can do. What you can do. Remember, set of finite sequences of natural number. First of all, you understand n star. First of all, you understand n star. N star is set of finite sequences of natural numbers. Set of finite sequences of natural numbers. Of natural numbers. Is this clear? Set of finite sequences of natural numbers. Finite sequences of natural numbers. In n star, this type of elements you have. For example, see this sequence. Okay, remember sequence. Sequence will belong to n star. For example, tell me, is this a sequence of natural numbers? I am giving you. Is this a sequence? Like, for example, tell me, is this a sequence? Look at this and tell me, is this a finite sequence of natural numbers? Is this a finite sequence of natural numbers? Look at this. This is a finite sequence, right? This is a finite sequence of natural numbers. Understood? Did you understand the set? First you understand the set. First you understand the set. So remember, this will belong to n star. Is this clear? This will belong to n star. This is one element in n star. Is this clear? This is one element in n star. This is one element in n star. Let me know, did you understand? What is n star? Did you understand? In n star, you have finite sequences of natural numbers. Finite sequences of natural number. This is natural number, natural number, natural number, natural number, natural number. So finite sequences of natural numbers. Understood? So remember, this belongs to n star. This will belong to n star. Okay, for example, I can say, like, for example, I can say 1, 2, 3, 4, 5. Okay, this will also belong to n star. Is this clear? Let me know. For example, this one, this will also belong to n star. Finite sequences of natural numbers. Okay, finite sequences. Finite sequences. So like this, I hope you understood. Okay, for example, 1 to 100. 1 to 100. This sequence, consider this sequence. This will also belong to n star. Okay, so this is what your n star is. Now this n star is countable. How to prove it? This n star is countable. This n star is countable. What is the definition you will use to prove this is countable? Your favorite, definition 3. Very good. Very good. You can prove it using definition 3. You can easily prove it using definition 3. Using definition 3. Yes or no? We can prove it using definition 3. Is this clear? See, some student is asking, these symbols, do they belong? No, no. This is just to explain. This is just to explain that this is the sequence. Okay, this is just to explain that this is the sequence of finite. This is just a, I can say this is a sequence of natural numbers. This is a finite sequence of natural numbers. Okay, so in your n star, see, in your n star, if you look at n star, in n star, every element will be like this. See, this will be a single element. Please understand. Okay, this is just to represent that this is a single element. Is this clear? See, this is just to represent that this is a single element. 58. Okay, 1. This is just a single element. Is this clear? And remember, this is another element. Remember, this is another element. Are they different sequences or not? These two sequences, are they same or different? These two sequences, are they same or different? Yes, they are different. Okay, remember, in a sequence, order matters. So remember, these two sequences, look at this. 1, 2, 3. This belongs to n star. And remember, this 2, 1, 3. This also belongs to n star. And remember, this 2, 2, 1, 3. This 2, 2, 1, 3. This also belongs to n star. Okay, is this clear? So for example, 2, 1, 2, 3, 3. This also belongs to n star. And all of them, these are different sequences. Okay, all these are different sequences. Is this clear? So remember, these are different sequences. These are different sequences. Is this clear? Because in a sequence, order matters, repetition matters. In a sequence, order matters, repetition allowed. Repetition matters. Repetition matters. Is this clear? In a sequence, order matters, repetition matters. Is this clear? Let me know. So these are different sequences. For example, if you look at these two sequences, these are also different. Like these two sequences, they are also different sequences. Okay, they are also different sequences. So because in a sequence, remember, in a sequence, order also matters, and you can see repetition also matters. Okay, so this is the sequence that belongs to n star. This is a sequence that belongs to n star. This is sequence that belongs to n star. Now you can prove that n star is countable using the definition 3. This is your favorite definition if you want to prove. So tell me, how will you prove? How will you prove using this definition 3? How will you prove? Let me know. Using the definition 3. Very good. Summation. Very good. You can assign summation wise. See, this is your set of natural numbers. Okay, this is the set of natural number 1, 2, 3, 4, 5, 6, and so on. Okay, so what you can do, you can assign summation wise. This is your n star. This is your n star. Let's assume this is the n star. This is the n star. So what you can do, see, to this one, what you will assign? To this one, you will assign those sequences whose summation is 1. Yes or no? You will assign those sequences. Those sequences. Remember, you have finite sequences only. Agree or not? In this n star, you have finite sequences. In this n star, you have finite sequences. You have finite sequences of natural numbers. You have finite sequences of natural numbers. Okay, so what you can do? To this one, you can assign those sequences whose summation is 1. Agree? Those sequences whose summation is 1. Whose summation equal to 1. How many such sequences are there? And here you can assign those sequences whose summation 4. Here you can assign those sequences whose summation is 4. Okay, is this clear? Let me know. Did you understand the idea? Did you understand the idea? Okay, and so on. Did you understand the idea? So tell me, for example, if I do like this, then how many sequences I will assign to 1? How many sequences I will assign to 1? To this one, what will be assigned? Which sequences are assigned to 1? Only this sequence will be assigned, right? Is there any other sequence which I can assign to 1? Is there any other sequence which I can assign to 1? No, this is the only sequence which will be assigned to 1, right? Agree? This is the only sequence that will be assigned to 1. Okay. How many sequences will be assigned to 2? How many sequences can you assign to 2? See, you can assign this sequence. You can assign 1, 1. This sequence also you can assign. That's it. Only these sequences you can assign to 2. Okay. Tell me about the 3. To this 3, what you will assign? To this 3, what sequences you can assign? To this 3. See, to this 3, you can assign this sequence. You can assign 2, 1 this sequence. You can assign 1, 2 this sequence. And you can assign 1, 1 this sequence. Agree? Yes or no? So how many sequences you will assign to 3? How many sequences you will assign to 3? Let me know. How many sequences you will assign to 3? So this is a finite. This is a finite set. How many elements? Only 4 elements. Okay. And so on. I hope you understood. Please tell me, did you understand what is happening here? Okay. How I am doing this? So finally, you tell me, can you notice? If I do like this, can I say every element will be covered? Okay. If I do like this, okay, 2 things you tell me. Okay. Just answer 2 questions. Just answer two questions. In the definition 3, answer two questions for definition 3. For definition 3, the definition 3 of countable set. Okay, so answer two questions. What are those two questions? The first question is every element covered? Is every element of n star covered? Is every element of n star covered? Tell me, is every element of n star covered? Let me know. And the second question you will ask, that is, to every natural number, are we assigning a finite set of elements? 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 Okay, just answer these two questions. Are you getting my point? In the definition 3, these two questions we need to answer. Agree? We need to answer these two questions. That is every element of n star covered? Did we cover every element of n star? And to every natural number, are we assigning finite set of elements? Okay, so tell me the first question. Is every element covered of n star? For example, if I give you this sequence, okay, consider this sequence. I am giving you this sequence 2, 2, 3. Okay, I can say 1, 50, 3, 1, 2. Okay, tell me, is this sequence covered or not? Is this sequence covered or not? What will be the pre-image of this? Just tell me, is it covered? Is this sequence? Remember, this is element in n star, right? See, this is element in n star. This belongs to n star. Okay, is this covered? The answer is yes. The answer is yes. Who is covering it? Okay, who is covering it? By n equal to, just do the summation. Just do the summation. So who is covering it? Just do the summation. Please tell me, who is covering it? Let me know. So you can see, like, this is 5. So 5, 10, 10, 60 and 10. That is 70. Yes or no? 74, right? Can I say? It is covered by 74. Very good. Okay. So you can see, is this element covered? Yes, this is covered by n equal to 74. So is every element of n star covered? The answer is yes. The answer is yes. Yes or no? And tell me the second question. Tell me the second question. Can I say to every element we are assigning only one element, finite number of elements? So this question we have seen, I can say this is correct. What about this question? To every n, are we assigning a finite number of elements? To every n, are we assigning a finite number of elements? And this is also correct. Yes. And this is also correct. The answer is yes. And here also the answer is yes. So both the places answer is a yes. Correct? Agree? So this is the simple idea. You can notice, to every element we are assigning only finite number of elements. For example, to 4, what we are assigning? Let me know. How many elements we are assigning to 4? See, to 4 you are assigning this sequence. Okay, what you are assigning? You are assigning this sequence. You are assigning this sequence. Okay, these sequences you are assigning. What else you are assigning? Tell me. To this 4. You are assigning, for example, 1, 1, 2. Okay, for example, you are assigning 1, 2, 1. For example, you are assigning 2, 1, 1. Okay, what else? What else you are assigning? For example, you are assigning 1, 1, 1, 1. This also you are assigning. So anyway, you can easily notice a finite number of elements you will assign. A finite set you are assigning. Yes or no? You are assigning a finite set. Agree with me? Please tell me. Okay. So can you check? Is there any other element which I can assign? Is there any other element? Yes, 2, 2 I can assign. Very good. 2, 2 I can assign. So the point is simple, that finite set we are assigning. We are assigning a finite set. Is this clear? Please tell me. Okay. So this is the idea. I hope you understood. Okay. So like this and so on. So like this. To every element we are assigning a finite set. To this 6 also, we are assigning a finite set. We will assign a finite set. Okay. To this one also, you are assigning a finite set. So that's it. Hence proved. What we have proved? Hence proved. What did we prove? Tell me. What did we prove? Hence we have proved that this n star is countable. This n star, this is countable. And what is n star? Remember, this is a finite set of finite sequences of natural numbers. Set of finite sequences of natural numbers. Natural numbers. Okay. So this is countable. This is finite sequences of natural numbers. Is your definition 3 favorite? After this question, can you say that definition 3 is awesome? And this definition 3 you will not find in the standard books. I found this definition 3 in a research paper. I told you. In our lectures, we have already covered it. Okay. You can watch on the Go Classes YouTube channel. You can watch complete countability. Complete countability lectures. All the lectures are available on the Go Classes YouTube channel. You can watch. Okay. We have already seen what is definition 3. And I hope this is your favorite now. Okay. Very easily you can solve the questions using definition number 3. Now let's solve this question. This is TIFR Computer Science 2015 question. Tell me the answer for this question. Sigma 1 is given to you, that is unary alphabet. Okay, that is 1-letter alphabet. Sigma 2 is given to you, that is binary alphabet. Okay. Now, a language over an alphabet, that is set of finite length strings. What is a language? Language is a set of finite length strings. Okay. Now, L1, L2, these are set of languages over sigma 1, sigma 2. Remember, L1 is a language or set of languages? Please tell me. L1 is a language or set of languages? Let me know. L1 is set of languages. Yes or no? Notice. L1 is set of languages. Okay, L1 is set of languages over sigma 1. L2 is set of languages over sigma 2. So please understand that your sigma 1, that is given to you, that is unary alphabet. And what is L1? L1 is set of all languages. L1 is a set of all languages over sigma 1. Okay, L1 is set of all languages over sigma 1. Is this clear? So tell me. So can I say that you can easily notice from this sigma star, from this I can say sigma 1 star, that is set of all strings. Yes or no? That is set of all finite length strings. That is set of all finite length strings, correct? Agree? Yes or no? This sigma 1 is whole star. This is set of all finite length strings. So this will be countable. We have already seen whatever alphabet you take, sigma star is always countable. Whatever alphabet you take. So remember this point. Whatever alphabet you take, it does not matter. Whatever alphabet you take, any alphabet sigma you take, it does not matter which alphabet you are taking. Whatever alphabet, you can take unary alphabet, you can take binary alphabet. Okay, you can take any alphabet. For example, you can take English alphabet. Okay, whatever alphabet you take, these two things will happen. What is that? First, sigma star will always be countable. Sigma star, this is set of all finite length strings. This will be countable because this is set of strings. This is set of all strings. Okay, this is set of all strings. This is countable. And what is power set of sigma star? What is power set of sigma star? That is set of all languages. That is set of all languages. Set of all languages. Okay, set of all languages. That will be uncountable. That will be uncountable. That will be uncountable. Okay, it does not matter which alphabet you are taking. It does not matter which alphabet you are taking. Sigma star is always countable, and set of all languages, that is always uncountable. So here also, if you have this unary alphabet, it does not change anything. Remember, if you have unary alphabet, then also I can say this sigma 1 star, this will be countable. This will be countable. Okay, this will be countable. And remember, this L1, this will be uncountable. This L1 will be uncountable. Okay, is this clear? Tell me why sigma star is countable. Why this? If your sigma, if you are taking this sigma equal to this, then why this sigma 1 star is countable? Because this is set of strings. Yes or no? This is set of strings: a square, a cube, a power 3, a power 4. Okay, yes or no? You can create a bijection. You can create a bijection. You can create a bijection between sigma star and set of natural numbers. You can create a bijection. How will you create a bijection? Tell me. You can create a bijection between set of natural numbers and sigma star. How will you create a bijection? This is the bijection you can create. This is the bijection you can create. This one-to-one correspondence you can create. So tell me, what is FW? Or I can say, what is F a power n? What is that? What is F a power n? That is n plus 1, right? Yes or no? F a power n, that is n plus 1. And this is bijective mapping. This is bijective mapping, right? Yes or no? This F is bijection. This F is bijective mapping. This F is a bijective mapping. So you can see this sigma star. Okay, this sigma 1 star, this is countable. Okay, so remember this sigma 1 star, this is countable. This is countable because we can create bijection between set of natural number and sigma star. This is bijection. Okay, this bijection we have created. We have created this bijection, this bijective mapping we have created. So this sigma 1 star, this is countable. Okay, simple, right? Yes or no? Very simple. Now you can easily see this sigma 1 star, this will be countable. Is this infinite? Is this infinite? Tell me. Is this infinite? This set. This is countable infinite set, right? Yes or no? This is countable infinite set. Because this is infinite set. You know, this is infinite set. Okay, this is an infinite language. Now tell me, what Cantor says? What Cantor says? Tell me. What Cantor's theorem? From Cantor's theorem, what we have seen, if you remember, from Cantor's theorem, what we have seen, that if S is any infinite set, if S is any infinite set, whatever infinite set you take, if S is any infinite set, then what will be PS? Then PS is always uncountable. Yes or no? Then PS is always uncountable. Correct? This we have already seen in the Cantor's theorem. In the Cantor's theorem, we have already seen this, that if S is any infinite set, this S can be any infinite set. Okay, if this S, this is any infinite set, then power set of S is always uncountable. Okay, now you can easily notice this is infinite set. This is infinite set. So tell me, so what will be power set of sigma 1 star? That is given to you. That is uncountable. Yes or no? That is uncountable. Power set of sigma 1 star, this will be uncountable. And in this question, power set of sigma 1 star, that is L1. That is set of all languages. That is set of all languages. That is set of all languages over sigma 1. So very simple. Set of all languages. And that is uncountable. Is this clear? This is a uncountable. Similarly, you can do for sigma 2 also. What is sigma 2? Tell me, what is sigma 2? Let's see. Sigma 2, that is A, B, that is binary alphabet. Okay. And what is L2? This is set of all languages over sigma 2. Similarly, you can notice this sigma 2 star, set of all binary strings. Okay, that is countable. That is countable infinite. That is countable infinite. Set of all strings. This is set of all strings. This is countable infinite. Okay. Now, because this is infinite, so what will happen? Because this is infinite, so what will happen? So the power set of sigma 2 star. So the power set of sigma 2 star, that will be uncountable. That will be uncountable. Yes or no? Okay. And in this question, L2 is power set of sigma 2 star. In this question, L2 is power set of sigma 2 star, which is set of all languages. This is set of all languages. Set of all languages. Okay. And that is uncountable. And that is uncountable. That is uncountable. So this is the answer. So for this question, what will be the answer? Please tell me. Please tell me what is the answer. So here you can notice L1, L2, both are uncountable. Okay, both are uncountable. So none of them is countable. So the answer will be option E. None of them is countable. What is the common mistake here? What is the most common mistake that people will make in this question? What is the most common mistake? Let me know. See, for this question, the answer will be option E. L1, L2, both are uncountable. But what is the most common mistake people will do? Some students, what they will do? Most common mistake in this question. What will be that? Anyone? Anyone want to tell me what is the most common mistake possible in this question? See, in this question, some students, they will think, okay, L1 is a language. This is what they will think. Some students will think that L1 is a language, L2 is a language, every language is countable. Okay, this is the common mistake people will make. They will think L1 is a language. They will think L1 is a language and they will think L2 is a language. And every language is countable, that we already know. That we already know. Every language is countable. Every language is countable. Okay, yes or no? Every language is countable. So this is the common mistake people will do. That they will think that L1 is a language, L2 is a language. And this is wrong, remember. Is this clear? This is a mistake. So this is wrong. Because the question is saying what is L1? See, read the question properly. L1 is set of all languages. L1 is set of all languages. So remember, L1 is not a language. L1 is not a language. L1 is set of languages. L1 is a set of languages. L1 is set of languages, not a language. L1 is not a language. L1 is not a language. Clear? L1 is not a language. So very simple. The answer will be option E. Now let's move on. Tell me the answer for this question. This is UGC NET Computer Science December 2015 question. Let's solve it. Which of the following statements are not true? See, the question is asking not true. Okay, which of the following statements are not true? Now, what we are saying, what we are having, the set of negative integers is countable. This is true, right? Set of negative integers is countable. Why? Tell me why. See, integers is countable, we know. This integers, this is countable. And subset of countable set is countable, right? Subset of countable set is countable. Subset of countable set is countable. Yes or no? So you can see that your set of integers, that is countable, and subset of countable set is countable. So you can easily see that set of negative integers, that is countable. That is true. What about this? Set of integers that has multiple of 7 is countable. Yes, this is also true. Because this is also subset of C. Option A is a subset of Z. Option B is a subset of Z. Okay, option A, option B, these are subset of Z. What about option C? Set of even integers. That is also true. Because option C is a subset of Z. Yes or no? See, option C is a subset of Z. Remember, integers is countable. Set of all integers is countable. Subset of countable set is countable. So I can say option A, option B, option C. These are true. What about this? Set of real numbers between 0, 0.5. This is false. This is false. Yes or no? Set of real numbers between 0, 0.5. This is false. We have already seen this. That if A, B are real numbers, if A is a real number, B is a real number, and A is not equal to B, and A is not equal to B, then set of real numbers between A, B, that will be uncountable. Yes or no? Then set of real numbers between A, B, set of all real numbers between A, B is uncountable. Is this clear? This we have already seen. This is a standard result. That if you have two real numbers, A, B, these are two real numbers, where A is not equal to B, where A is not equal to B, then set of all real numbers between A, B, that is uncountable. Okay, so I can say, so similarly you can notice set of real numbers between. So easily you can see set of real numbers between 0, 0.5, that is also uncountable. That is also uncountable. We can prove it using Cantor's diagonalization proof. Yes or no? We have already proven. Agree with me? This we have already seen. You can prove it using Cantor's diagonalization proof. That set of real numbers between a comma b, where a is not equal to b, where a is not equal to b, set of all real numbers between a comma b, that is uncountable. So set of real numbers between 0, 0.5, that is uncountable. You can prove it using Cantor's diagonalization argument. We have already seen this in our lectures. Okay, so very simple question. Which statement is not true? So option B, option D is false. Answer will be option D. Okay, let's move on now. Let's solve this question. This is UGC NET Computer Science September 2013 question. So tell me the answer. First you tell me as to the set of all Turing machines. Set of all Turing machines, that is countable. Yes, set of all Turing machines is countable. Because every Turing machine you can encode as a string. See, every Turing machine you can encode as a string. So set of all Turing machine, that is same as set of all Turing machines. That is just set of strings. Yes or no? This is just set of strings. Because every Turing machine we can encode as a string. This Turing machine we can encode as a string. As a string. Okay, we can encode as a string. So when I say set of all Turing machines, what that means? So set of all Turing machines, that is same as set of strings. Set of strings. And that is subset of sigma star. That is subset of sigma star. Set of strings, that is subset of sigma star. Sigma star is countable. Sigma star is countable. Subset of countable set is countable. Subset of countable set is countable. So this will be countable. So set of all Turing machines, that is countable. Okay, that is countable infinite. This is countable infinite. So simple. So this statement is actually true. The question is asking which is true. S2 is definitely true. What about S1? L2 minus L1 is recursive enumerable, where L1 is recursive, L2 is recursive enumerable. Is this statement true? Is S1 true? See what S1 is saying. S1 is saying that L1 is recursive. L1 is REC, recursive language. L1 is recursive language, means REC. And L2 is recursive enumerable language. That is recursive enumerable language. Okay. The question is saying that if L1 is recursive, L2 is recursive enumerable, then L1 minus L2 will be RE. Then L1 minus L2 will be RE. Is this statement true? Is this statement true? L1 is recursive, L2 is recursive enumerable. Then can I say that L1 minus L2 will be RE? Sorry, the question is saying L2 minus L1. Okay. The question is saying L2 minus L1 is RE. Then can I say L2 minus L1 is RE? Okay. See, the question is saying L2 minus L1, that is RE. L1 is recursive. You can see L1 is recursive. L2 is recursive enumerable. The question is saying L2 minus L1 is RE. Is this true? Is this true? See, you already know this. You already know if you have set A, B, then what I can say A minus B, what is that? How can I write A minus B? That is A intersection B complement. Yes or no? Agree? So A minus B, that is A intersection B complement. So here what I can do? Here I can say L2 minus L1, that is L2 intersection L1 complement. You tell me one thing. L1 is recursive language. So what is the complement of recursive? Recursive complement. What is that? Complement of recursive language is recursive. Complement of decidable language is decidable. Yes or no? See, this is your table. This is the decidability table. You can easily notice in this, this is the closure property table. This is the closure property table. You can notice in this closure property table, you can notice this is your recursive. This is your recursive. Okay, so you can see that complement of recursive is recursive. Actually, recursive languages are closed under all the standard operations. Can you notice? Recursive languages. Recursive means decidable. Recursive means decidable. Okay, this REC language. That means recursive language. REC means recursive. Okay, and that is decidable. Recursive means decidable. That is a decidable language. Decidable means recursive. Recursive means decidable. These two things are same. Can you notice that? These recursive languages, these are closed under all the standard operations. These are closed under all the standard operations. Union of two recursive language is recursive. Intersection of two recursive language is recursive. Complement of recursive language is recursive. So you can see these recursive languages, they are closed under all the standard operations. Yes or no? Is this clear? So easily you can see that recursive complement will be recursive. So can I say this is recursive? L1 complement. Can I say this is recursive? Yes or no? This is recursive. Remember, this is recursive. And this is RE. This is RE. Okay, you tell me now. RE intersection recursive. What you can say about that? See, L2 minus L1, that is minus L1, that is L2 intersection L1 complement. Now, this L1 complement, this is your recursive. Because recursive complement is recursive. Every recursive language is RE. Yes or no? Every recursive language is RE. Every recursive language is RE. Okay, and this is already RE. So what you can say about RE intersection RE? What you can say about RE intersection RE? That will be RE. RE intersection RE, that will be RE. You can easily notice here. See, set of recursive enumerable languages. Set of recursive enumerable languages. They are closed under intersection. They are closed under intersection. Yes or no? Set of recursive enumerable languages. They are closed under intersection. So, RE intersection RE, that is RE. Yes or no? RE intersection RE, that is RE. Is this clear? RE intersection RE, that will be RE language. Because set of, you can see, these recursive enumerable languages, they are closed under intersection. So finally, I can say here, RE intersection RE, that will be RE. Okay, so very easily you can see L2 minus L1 will be RE. Yes, that is correct. Yes or no? L2 minus L1 is RE. This is true. This statement is true. Please tell me, did you understand this? Let me know. See, the question is very simple. In the S1, we have basically, we are asking what is RE minus REC. What I can do, I can write it RE intersection REC complement. Okay. REC complement is REC. REC complement will be REC. Okay. So I can say that this will be RE intersection REC. Remember, every REC is RE. Every REC language is RE. Every recursive language is recursive enumerable. Every recursive language is recursive enumerable. So finally, you have recursive enumerable intersection recursive enumerable, and that will be RE. Okay, so this statement S1 is also true. So both statements are true. Is this clear? Both the statements, these are true. Let me know, did you understand this? Please tell me. Let me know, did you understand this? Is this clear? Now let me ask you one variation. In the same question, if I ask you, L1 minus L2, see, L1 is recursive, L2 is RE. So L2 minus L1 will be RE. This is true. This we have already seen. Okay, means RE minus REC, that will be RE. This statement is true. That will be RE. This statement is true. But what about L1 minus L2? What can you say about L1 minus L2? Let me know. What can you say about L1 minus L2? L1 minus L2. This will be RE. This statement is false. This statement will be false. Why? See, easily you can notice this L1, this is RE. Sorry, this is REC. And L2 is RE. Now, what is REC minus RE? What is REC minus RE? What is REC minus RE? That will be REC intersection RE complement. But remember, RE languages are not closed under complement. RE languages are not closed under complement. You can see the set of RE languages, they are not closed under complement. So RE complement may or may not be RE. RE complement may or may not be RE. Remember, if you have a RE language, its complement may or may not be RE. May or may not be RE. Is this clear? If you have a RE language, its complement may or may not be RE. So this is the reason I can say this may or may not be RE. This may or may not be RE. May not be RE. Okay, this may or may not be RE. So that is the reason I am saying that this L1 minus L2, this will be RE. There is no guarantee. Okay, there is no guarantee. Is this clear? Let me know, because RE complement that may or may not be RE. This itself can be not RE. For example, this can be not RE. Remember, this can be not RE. Is this clear? This can be not RE. Please tell me, is this understood? So simple, you can see this is your question. So we have seen this. So this was our UGC NET question, and for this I can say both statements will be true. Set of Turing machines, that is countable, that is true. Also you can see RE minus REC, RE minus REC, RE minus REC, that is RE. This is also true. Okay, this is also true. Using closure properties, you can easily notice. This is your closure property table. Okay, and using this, you can easily solve this S1. So the answer will be both statements are true. Let's solve this question. This is UGC NET Computer Science January 2017 question. Tell me the answer. Let me know the answer for this question. Which of the following statements are false? The question is asking which are false statements. Every context sensitive language is recursive. Every context sensitive language is recursive. This is actually true. This is true, right? Yes or no? Okay, because you can notice every regular language, these are the regular languages. Every regular language is CSL. Okay, or I can say that is CFL. Every regular language is CFL. Every CFL is CSL. And every CSL is recursive. Every CSL is recursive. And every recursive is RE. Okay, every recursive is RE. Every recursive is RE. So you can easily see every CSL is recursive. This is actually true. Every context sensitive language is recursive. That is actually true. What about the next? Set of all languages that are not RE. Tell me. Set of all not RE languages. Set of all not RE languages. Set of all languages that are not RE. Set of all not RE languages. That is uncountable, right? This is false because that will be uncountable. So this statement is false. What about the statement C? The family of RE languages is closed under union. This is true. You can notice RE languages are closed under union. See, RE languages, they are closed under union. They are closed under union. Okay, RE union RE, that will be RE. Okay, so this is true. The family of recursive enumerable languages, they are closed under union. This is true. The family of recursive enumerable and recursive languages are closed under reversal. Are closed under reversal. This is also true. This is also true. You can notice under reversal, RE languages are also closed and REC languages are also closed. Okay. See, recursive languages, these are the decidable languages. Recursive means decidable. See, decidable languages are closed under all the standard operations. All these standard operations, union, intersection, set difference, complement, concatenation, intersection with regular language, clean star, clean plus, reversal. All these are standard operations. Okay, remember, these are all of them. These are standard operations. Okay, so you can see decidable languages, they are closed under all the standard operations. Okay, and these RE languages, they are also closed under most of the standard operations except these two. RE languages, okay, recursive enumerable languages, they are also closed under most of the operations. They are also closed under most of the operations except set difference and complementation. So you can see the family of recursive enumerable and recursive languages are closed under reversal. This statement is true. So which statement is false? Tell me. Which statement is false? The answer will be option B. Because remember, set of not RE languages is uncountable. Okay. set of not RE languages, that is uncountable. So very simple. Now let's solve this question. Tell me the answer. Tell me the answer for this question. This is UGC NET June 2015 question. Let me know the answer for this question. The set of recursive enumerable languages is countable. Set of all RE languages. Set of all RE languages. Yes, that is countable. That is true. The question is asking true statement. This is true statement. Set of RE languages, they are countable. This is true. What about S1? What about S1? If L1, L2, they are recursive languages. They are recursive enumerable, sorry. They are RE languages. L1, L2, they are RE languages. Okay. Then their union is also RE. Their intersection is also RE. Yes, that is true. That is true. Okay. That is also true. You can see RE languages are closed under union, comma, intersection. Okay. You can see RE languages. You can easily see here. See this. RE languages, set of RE languages, recursive enumerable languages, they are closed under union. They are closed under intersection. They are closed under union, comma, intersection. So RE union RE, that will be RE. RE intersection RE, that will be RE. So you can see L1 union L2, L1 intersection L2, they are recursive enumerable. That is true. So the question is asking which statement are true? Both are true. Both S1, S2 are true. Okay. So very simple. So these are all your UGC NET questions. Okay. I hope you understood all these things. So please tell me, all the questions we have seen, all the UGC NET questions, all these things we have seen, please tell me, do you have any doubt? Let me know. In all these questions, do you have any doubt? Let me know. So far, every question that we have seen, do you have any doubt? This is Stanford question, so let's take it. This is Stanford question. So tell me what will be the answer. See, this is a Stanford, very simple question this is. So tell me what will be the answer for this question. For any set A, for any set, remember, for any set A, whatever set you take, cardinality of A is equal to cardinality of A. Okay, how can you prove it? For any set A, cardinality of A is equal to cardinality of A. How will you prove it? See, if you want to prove it, you can create a bijection, right? You can create a bijection. How can you prove it? You can create a bijection. Remember this definition. When can I say if you have set A, comma B? If you have set A, comma B, when can I say they have same cardinality? When can I say they have same cardinality? If and only if there exists a bijection. If and only if there exists a bijection. If and only if there exists a bijection between A, comma B. Yes or no? If there exists a bijection between A, comma B. Very simple. Agree? Now tell me, if you have set A, can you create a bijection? Okay. From set A to set A, does there exist a bijection? Does there exist a bijection? From set A to set A, does there exist a bijection? Let me know. Does there exist a bijection? The answer is yes. The answer is yes. This bijection exists. Fx equal to x. Yes or no? This bijection exists. This bijection exists. You can notice this is bijection. Okay, this is bijection. Tell me one more question. Tell me one more question. I want to ask one more question. Can I say every mapping is bijection? From A to A. From A to A, can I say every mapping is bijection? Can I say every mapping is bijection? From A to A, from A to A, can I say every mapping is bijection? Can I say every mapping is bijection? The answer is no. Can I say every mapping will be bijection? The answer is no. For example, if you have this 1, 2, 3 and this 1, 2, 3, consider this mapping. I can give you this mapping. Just consider this mapping. Is this mapping a bijection? Tell me. Is this mapping a bijection? This mapping F is not bijection. Yes or no? This mapping F is not a bijection. Is not a bijection. Is not a bijection. So remember, there exists a bijection. Is this clear? Please understand that from A to A, there exists a bijection. There exists a bijection. This bijection exists. This bijection exists. But can I say every mapping will be bijection? But can I say every mapping will be bijection? No, I cannot say every mapping will be bijection. So what will be the answer for this question? For every set, cardinality of A is equal to cardinality of A. Which of the following is right way to approach this proof? How can you prove it? Which of the following is true? Find a bijection. Very good. So the answer will be option A. Okay, find a bijection. The answer will be option A. Is this clear? Can I say every function will be a bijection? Can I say every function will be bijection? No. Can I say every mapping will be bijection? No. Okay, there is nothing to prove it is obvious. Can you say? Can you say it is obvious? There is nothing to prove. No. Okay, you can prove it using the bijection. Okay, you can prove using bijection. If you want to prove set A equal to set C, if you want to prove cardinality of set A equal to cardinality of set B, if you want to prove this, then just create a bijection between A, B. Okay, so very simple. So the answer will be option A. For this question, the answer will be option A. Option A will be the answer. Okay, so this is the idea. I hope you understood all these things. So that's enough for this session. Please tell me, did you understand everything? Let me know. Please tell me, did you understand every question that we have seen? The complete countability we have seen, everything we have seen in the countability. We have seen all the GATE exam questions, all the TIFR exam questions, all the NET exam questions. We have seen countability results in theory of computation. We have seen Cantor's diagonalization proof, 3 definitions of countable set. Okay, Cantor's theorem. We have seen consequences of Cantor's theorem, infinite levels of infinity, Hilbert's hotel, Hilbert's grand hotel. Everything we have seen. Okay, this countability, in this countability chapter, every concept we have seen. So please tell me, are you comfortable? Let me know. In this countability, we have seen every concept. You can see countability is over. I hope you enjoyed countability and did you learn? Please tell me. Did you understand countability? In this countability, we have seen everything you can notice. Okay, we have seen cardinality definition, the results related to cardinality, countable set, uncountable set, Cantor's diagonalization proof, 3 definitions of countability. Okay, theorems related to countable set, Cantor's theorem and its consequences, and countability results in theory of computation. So everything we have seen. Okay, and I want to tell you that this countability, this complete countability playlist, you can notice countability complete playlist. See this countability complete playlist. Okay, this is available on the YouTube channel, on the Go Classes YouTube channel. Okay, on the Go Classes YouTube channel, on the YouTube, you can search Go Classes Countability playlist. Okay, so this playlist, this complete playlist is available on the Go Classes YouTube channel. You can find it. Okay, all the lectures are available here. You can notice. Okay, so I hope you understood, and we have done all the questions. We have solved all the questions. So if you understood countability, then please comment and share your feedback on the Go Classes YouTube channel. Okay, so this playlist is available. All the lectures are available. So please share your feedback. Please comment, like, and share. Okay, so that we can reach more students. Okay, see, in this playlist, we have covered every proof, every variation, every type of question, every proof, everything we have seen. This is the, I can say, complete course of countability. Okay, this is complete course of countability. Okay, this much, I can say, this much is enough for any exam. You can attempt TIFR exam, NET exam, GATE exam, interview, whatever exam you attempt, this is enough. Okay, even if you attempt subjective exam, let's assume you are attempting a subjective exam, DRDO. Okay, DRDO is a subjective exam. So in the DRDO exam, if they ask you some proof that this happens. Okay, prove that set of real numbers is uncountable. Prove that n cross n is countable. Okay, prove Cantor's theorem. So whatever they ask you, you can do that. So this playlist, this is enough for countability. This is your countability complete course. Okay, so please share your feedback on the Go Classes YouTube channel. Please comment and share your feedback. Okay, thank you everyone. Thank you so much.